rest energy is the energy objects have because they exist in space-time. It's the energy objects have because they exist. Okay? Because objects exist in space-time, they have something called rest energy. Okay? And it has to do with an object's mass. So it turns out the amount of rest energy an object has is dependent on how much mass it has. Objects with more mass have more rest energy. Objects with less mass have less rest energy. Okay? So a proton has much less rest energy than you do. You have lots of rest energy, which makes sense. You're in high school, right? Of course you have lots of rest energy. So it's important to note more for the, this is actually for the last unit of this semester. This matters more when we get to thermodynamics. Rest energy is generally useless energy. It can be used, but it's very difficult to use it. And so we usually think of rest energy as unusable energy, but there is an example where it can be used. So what's the equation that relates these things? You've all seen this equation before. E equals mc squared. Here you go. This is like that one equation that you throw out when you want to sound smart, right? Since you were a small child. I honestly, this is going to sum up me perfectly, right? I remember where I was when I saw this equation for the first time. I was in the cafeteria at school, in elementary school, in 5th grade. And they had this equation just up on one of the windows in the cafeteria. And I was like, what's up with this? What's going on with this equation? And I asked all the teachers, and they were like, I don't know what it is. It's just up there. And so I had to look and look and look. I had to go to the library, like several different libraries, before I could find any information. Because again, this is pre-internet. It's not like I could search it online on Google. I had to go find a book. And nobody knew. They just had it up. And I was so cranky about this because they wouldn't, it drove me nuts. That's the equation. So, how do nuclear power plants produce energy? Nuclear power plants take 2 hydrogen. Yeah, well, actually, I'm thinking the sun. Let's do... Hold on. I think I have a question on here. I actually want to use the sun example for this. I'll change the question on the practice. It's an easy enough change. So instead of how do power plants produce energy, change it to how does the sun produce energy? Sorry, I prepped this question for the sun. I didn't actually read my own question. Good job, me. All right, the sun takes 2 hydrogen atoms and it smashes them together. And when it smashes them together, it creates 1 helium atom. Okay, so far so good. Hydrogen turns into helium. Great. Hydrogen is 2 protons, 1 proton. You add those 2 protons together, you get helium, which is 2 protons. Not shocking at all. Here's what is shocking. Okay? The mass of 2 hydrogen atoms, so the mass of 2 hydrogens is 2.01568. Atomic mass unit, so AMUs. The mass of 1 helium is 4.00260. Oh, I wrote the wrong thing. Hold on. I wrote the wrong number. That's my bad. I know what I did. So dumb. Sorry, I forgot to account for neutrons. Sorry, here we go. This number here. Okay, I want you to notice something about these numbers. They are not the same. Makes no sense, right? Why would I smash two things together and get a different answer? Okay? It would be like if you stood on a scale, if you had a mass of 120 pounds and you had a cat that had a mass of 30 pounds. It's a very large cat. If you held them together, you would expect to measure 150 pounds. It's like if you had 120, the cat had 30, and you hold it and it measures 148. Makes no sense, right? Why would you smash two things together and get a different weight? It's like if you were to eat a hamburger that weighs 2 pounds and you would not actually gain 2 pounds, you would gain 1.5 pounds. Why would that be? It doesn't make any sense. So, where does that energy go? Where does that mass go? So, what happens is the missing mass turns into energy. What happens is the mass that's lost when you go from one hydrogen into helium, that's essentially two hydrogens smashed together, that lost mass turns into energy. And that's why the sun produces energy, because it's constantly doing this. So the sun is actually lighter today than it was yesterday, because the sun has produced energy, and the energy has been released in the form of mass. So, how much mass is released? The answer is lots. Okay? When you talk about the mass change, it's a very, very small mass change. But the equation is E equals mc squared. So even if this number is very small, this number is very large. So it ends up balancing it out, even though this is not a very large amount of mass. Now, it's still going to be a small number, but that's for one single reaction. Okay? In the sun, it's not one reaction. It's billions of reactions at once. That's why the sun is so hot and bright. Because this amount of E is based off of a huge mass change because of it happening so many times. And c squared is an enormously large number, which makes this small mass much more magnified. So, number 5. There's another way to explain why light is bent by mass. So the example we used is light follows space-time, and space-time is warped. Here's the other explanation that I'm also fine with. Even though light is energy only, because of E equals mc squared, it acts like it has mass. Okay? Even though E equals mc squared, even though light is just energy, it acts like it has mass, because energy and mass are equivalent. So because energy and mass are equivalent, excuse me. Because energy and mass are equivalent, even though it does not have mass, it acts like it has mass. And that is another possible explanation for why gravity bends it, because even though it acts like mass, gravity can affect the mass, even though technically it doesn't have it. Okay? Okay, go ahead and, that gets us through those notes. Go ahead and work on the back page of the practice. I'm going to give you the rest of the period to work on this. In about 5 to 10 minutes, once I've gone around once to see if you have any questions,